physics and astronomy. A number of papers are being presented here, and some of them will be slightly technical, but the main themes are very important, dealing with current paradigms in astronomy and physics, which are closely intertwined, as you know. Our first speaker is Professor Larissa Lapershvili from the Institute for Theoretical and Experimental Physics in Moscow. She is a very brilliant physicist herself and closely collaborates with the Niels Bohr Institute in Copenhagen, which, as you know, is one of the world's leading research institutes. So, Professor Lapershvili will be speaking essentially on problems related to gravity-weak unification. Now, you know that there are these fundamental forces of nature like strong interaction, weak interaction, electromagnetism, and gravitation. Strong interaction is what keeps a proton and a proton together in the nucleus. Because two protons, if you only think of electromagnetism, they will repel and the nucleus breaks. But that doesn't happen because there is an even stronger interaction. Similarly, there is something called the weak interaction, which leads to the decay of various atoms, with neutrinos being ejected in the process. Now, gravitation, unfortunately, is one interaction that stands apart. It stands apart because it cannot be described in a unified manner with other interactions till today. But the attempt here is to give a combined description of weak interactions, gravitation, and so on. So I would request Mrs. Geeta to take over the proceedings.
Welcome you all to the Physics and Astronomy meet. We will be starting the lecture with Professor Larissa. She is from the Institute of Theoretical Physics, Moscow. She will be talking on Planck-scale physics, gravity-weak unification, and the Higgs inflation model. Welcome. I invite Professor Larissa.
I submit you a talk devoted to the quite new subject, new theory. The subject is Planck-scale physics, gravity unification, and the Higgs inflation model. Here you see authors. Professor Zita, Professor Wilson, and I am here.
Change.
how to change the second. Here you see contents. I shall speak about discrete space-time of the universe at the Planck scale and about predictions of non-commutativity. About random dynamics and multiple point principle, you will see. Rebansky's formulation of general relativity, gravity unification is the visible sector of the universe and then the invisible. Mirror world with broken mirror parity, U4 group for fermions, multiple point model and predictions of the top and fixed masses. And the last is new model of Higgs inflation from the false vacuum and the mirror Higgs. Yes. Now, at present time, a lot of physicists are keenly and persistently searching for fundamental theories at the Planck scale, at small distances of order of Planck length. And in this regard, we can classify all theories in two types of theory. First type of theories considers continuous space-time at the Planck scale. And second type of theories considers discrete space-time at the Planck scale. Among these theories, which consider continuous space-time, are ground unification theories, supersymmetry, superstrings, general relativity. But also there exist many theories which considers the space-time at Planck scale as discrete space-time. For example, Laurent Notaire from Paris considers scalar relativity with fractal physics at small distance. Or Heidenreich considers gravity as a crystal with defects. All Jan and Bjorn considers triangular gravity. Lattice models. But in this investigation, we prefer only two theories, which it is no, please, I don't know. Huh? No, then, is it better?
Yeah, little bit better.
I don't know. Yes. So we prefer only two theories. The first theory is of discrete space-time with non-commutative geometry. Is theory by Professor Siddharth, which, I'm sorry, the next, which was described very well in his book. In his book, The Thermodynamic Universe. And please next, because I can't speak everything, I shall be not in that. Please, next. Yes, and the second theory is random dynamics developed by Holger Nielsen and his collaborators of Niels Bohr Institute. It was published in 1985 year by Nielsen, Bennett and Brennan. And then was described very well in the book by Froger Nielsen. He has mistake Froger is 2T. Wilson in their book Origin of Symmetries. What is random dynamics? Random dynamics also is a theory of discrete space-time. It is lattice-like theory and random lattice-like theory, random lattice. And now a lot of efforts was spent to see ground unified theory, not very good. Because, next please. But ground unified theories has special axioms. If one axiom is changed, then the theory is changed and maybe becomes non-consistent. But random dynamics is alternative of this theory, because random dynamics is based on very general assumptions. Random dynamics are good. The fundamental laws of the nature are so complicated that it is preferable to think that at very small distances there are no laws at all. And our space-time is discrete and the physical processes are described randomly. Since the fundamental law of the nature is one which was randomly chosen by nature, and what the nature has chosen, it is this we see, the consequence we see in low energy limit of our experiment. Next, please. But here I want to return to that theory, and want to tell you that in this paper, the universal fluctuations, published, you see, in 1998, Professor Dark was first in the world, before Perlmutter's discovery and published in 1999, he predicted that cosmology constant is small of order squared Hubble ray, and dark energy, that is vacuum energy density of the universe, and dark energy is small of order, now it is astrophysical measurements, what it is in such small. And just prediction coincides with this astrophysical measurement. And he predicted the accelerated expansion of our universe after Big Bang. It's very, I think, Nobel Prize meant to say. Так, see that? What? Please, next. No, now we know that recent modern fuzzy space-time theory and also loop quantum gravity, they consider the space-time cutoff. The minimal, they consider received minimal length, quantum of space-time, minimal length, minimum time, minimum area, minimum volume. And if so, let us start with some system which has particles and randomly moving in this system, and the system has radius r, and we can consider n number of particles, and then average distances are divided on square root of n. Because of fluctuation, it is formula by Wellington. But we can consider, this is average distance L. But we can now, let us consider universe. Universe has radius, what you see, 10 in degree 28 centimeters. And if you have number of number of elementary particles, no, for example, mu 10 to in degrees 80, then Compton wavelength is of order 10 minus in degree minus 12, and it is math. Of order 1 math particles with mass 1 math. And their Compton length is 10 in degree minus 12 centimeters. But if we have the next place, but if we have one, no, the same is for time, yes, for time. This is no, I don't speak about this. Yes, but if you have quantum oscillators in the universe, they must be the number 10 in degree 120. But then the length is of order of Planck length. That is 10 in degree minus 33 centimeters. But if so, as it was shown by Siddharth, we have what? Fuzzy space-time, non-differentiable, as in general relativity. And if so, we must consider non-commutative geometry. And since this commutation relation is not zero, it is proportional to square L, minimum length, please. And then Snyder, in 1947, writes, it's no comma, I think, yes, comma here, writes the commutation relations with is this non-commutative space-time. And you see that it is not Heisenberg's, but has additional term. And then for momentum of particle has additional, is modified and has additional terms, and energy also has additional terms. And yes, please next. If so, then we have such a energy, no, resultant energy. It is energy old minus energy coming from non-commutativity. And this E2 prime, we can use Einstein's theory is related with mass F, but only for bosonic fields. Please next. If you have fermionic fields, this is plus. Here you see plus. So this E2 prime is minus MC, you know, it is light velocity, and B is bosonic fields, mass bosonic fields, and F fermionic. You see the different sign. And this formula this formula helped Professor Siddharth to identify this dark energy density as small. Vacuum energy density is described by 0 point fields, zero modes of degrees of freedom. And so vacuum energy density is huge. It was noticed by Professor Zeltovich from Russia. Please, and then this vacuum energy density is huge, and then cosmological constant is huge. And this problem was called by Steven Weinberg as the cosmological constant problem. But mysterious 0 point fields contribution, if you see astrophysical measure, is small. What is it? What that system predicts predicts that this lambda is small. Why? Because you have this non-commutative contributions in it. And no, I shall see this more in details later. And now what we shall see this problem. I only want to tell that if you want to see about non-commutative field theory, also it's good this paper. The next, please. And now random dynamics. I want to repeat that non-commutativity solves the problem of cosmological constant. It diminishes such a large value and gives small. We shall see. Our random dynamics. It doesn't know what lattice is at small distances. Maybe it is hypercubic lattice, or maybe random lattice, or string-like lattice, but it is described by lattice model. And Monte Carlo simulation of lattice indicates the existence of triple critical point. What does it mean? Because Monte Carlo simulation always sees on phase diagram the meeting of three phases, for example, Coulomb-like, total confining, partially confining, and they meet at one point which is triple point, critical point, triple point. But then Nielsen and his collaborator tell us that if we have more complicated field theories, and we can have multiple critical points, that is point in which many phases meet together. Please, the next. And then random dynamics has led to the assumption that it is quite possible for a quantum field theory to have several minima of the effective potential as a function of its scalar field. Random dynamic postulates there are many fake points in the universe with the same energy density, but all of them are cosmological constant, zero or almost zero. The second, please. This postulate corresponds to what we call multiple point principle. It was suggested in 1994 by Bennett Nielsen. The multiple point model is the base of our new model of Higgs inflation. Next. Now, I want to speak about gravity unification. Previously, we have constructed a model unifying gravity with weak SO2 gauge and Higgs scalar field. It was done by Chitaran Jantas and Ankartoriano from Helsinki and myself. It was published. This is archive. We developed this gravity unification according to this paper. It is Garrett-Lacey Smalling speciale, which gave general unification of gravity with gauge fields and Higgs boson. Next. And but constructing this gravity unification, we consider Prebansky four-dimensional gravity. And I want to tell you this story. What is Prebansky's four-dimensional gravity? Because only this formalism gives us to make unification. Now I remind you that originally general relativity was formulated by Einstein as dynamics of metric G-mu. And metric G-mu, as you know, has 10 degrees of freedom. Next, please. But Prebansky and then Ashtekar, Indian, they considered that gravity can be reformulated in any way, by any way. Plebanski made his theory in 1977, but his theory was forgotten. And 10 years nobody used it. And only Ashtekar developed the theory on new level. Please next. And please next. What is in the Plebanski formulation very interesting? That now he doesn't consider G as field, as variable, dynamical variable, as independent field. It considers spin connections and tetrads. What is now tetrads? I want, what is it now? Please. Now we consider such a thing. For example, you have curvilinear space and described by Gemini, metric Gemini. In each point of this manifold, you have tangential flat space. Minkowski, for example. Here you have coordinates x mu. Yes? X mu. X mu. But here you have on this tangential x, I. Mu has 0, 1, 2, 3 indices, time and special. And this has I capital 0, 1, 2, 3, but it is flat space, it is not flat. But then you can see the trans. The trans are dx I on dx plane. What? These are the trans. And Plebanski considers these independent variables, spin connection and tetrads, and his four-dimensional gravity is constructed from two forms of I, R, A, and E. Please say next. Here you see one form of A. A is spin connection, what this is, A mu, has two indexes in flat space. You will see one later. And E is also one form. And also considers a little bit more complicated theory by Plebanski, but I'm sorry. A is also given by Clifford algebra. Then gamma ij is the product of Dirac matrix in four-dimensional sense. Then eta ij is Minkowski matrix. Next. Then you have Watt interval, and Gemini is related with tetrads in such a way. But you know independent variable. And then he constructs two forms, B and F. What is B? B is wedge product of tetrads. What is wedge product? Maybe you know. It is necessary to construct antisymmetric combination of E and then multiply on dx mu dx mu. It is
Grassmann.
yeah, yes. And F I choose also two forms. Please next. And as this F mu I G is just field strength of spin connection. It is very similar to Young-Mills gauge field. Similar. And then Riemann-Karpman is related with this F mu. And he considers them B and F in the next. And then it is very famous DF gravitational theorem by Plebanski. It is gravitational action, which is given in such a way. No, maybe if you want, you can see our with Nilsson in archive. We have papers, and I can't speak too much. But then Prebansky considers two of them sources. Two versions are in cardinal space. It is given by star, Hodge star dualogration, what you see next. But in flat space, Soviet star, I'm sorry, people call Soviet star. It is such a dual, but it is the same, but in flat, it is so. And then Prebansky introduced self-dual and anti-self-dual components of spin connection. You see, please. But then if you consider these components, then these projectors give homomorphism that Lorentz group has two sum of two pieces. It is Lorentz, not group, Lorentz Lie algebra. Lie algebra, and here is what? Right and left. That is, there exist right and left Lorentz groups. Right and left well-known gravity. One gravity is constructed by self-dual spin connection, and the left is self-dual and right anti-self-dual. And also in terminology is such a thing that right is self-dual or right-handed, and left is anti-self-dual or left-handed. But and now right is right Lorentz group is constructed with self-dual A and no left and right by anti-self-dual. And it is easy to see that this self-dual, anti-self-dual, they have only this component non-zero. And then you have, instead of ij, you have only I index. I equal 1, 2, 3. Next. And then Prebansky considers only Prebansky's assumption that our ordinary well is self-dual. And he considers our, what is it, gravitational action by self-dual components. And sigma is related with B, with 2 form B. And but why we have this psi? Because of constraints. Because the degrees of freedom in Prebansky theory is 36. But Einstein has 10 degrees of freedom is life. And he introduces with Lagrange multipliers and constraints which diminish the degrees of freedom. Now the number of degrees of freedom. The next place. And then his assumption is that our world is self-dual, but anti-self-dual are zero, no right. And then he considers this the equivalence to Einstein-Hilbert theory. It is they are equivalent his and that. But I wanted to tell you before that we, also with Nilsson and Agatoriano, we considered not that the right well also exists. And we have two wells, ordinary well, left and right. near world. It is crucial for our field. Next, please. And then, again, in our paper, with Tassel-Toriano, we consider spin for foreign variant Plebansky action, little bit modified because we need Higgs fields, and G uni is overall unification parameter. Next, please. And then we write equation of motions for F, B, and phi, and B and phi are auxiliary fields. We can exclude them, exclude B, and write the what is this action, gravitational action as pure spin connection. Here is F only, no B more. And phi, of course, is for constraints, for right degrees of freedom. And you see it is wedge product explicitly is given in such a way, and we have chosen, it is our choice, we have chosen the constraints, ansatz, in such a way, and then this next. We consider the breaking of gravity unification into this, here is the algebra, this and to left. It is weak interaction group. And then our gravity A has three tags. Yes, now I want to use it. What is gravity? What is gravity unification? Please. Oh. Yes, then you have now spin connection as 8 by 8. Previously we had 4 by 4 matrix. Now we have 8 by 8 matrix. It is such a matrix that here is 8 by 8 matrix. Here is gravity. Here is SO2. Here is omega AB. It is spin connections of gravity. Here is AW MN, and here is of diagonal terms AN, and here also. This of diagonal term is given by Lisi and has such a given by such expression. Here is the product of what is it? Tetra and Higgs field phi. 1 phi. Next, please. And as a result, we received such an action. As a result of gravity, result breaking of gravity breaking. And you see here, this term is scalar field squared on R. R is Riemann scalar curvature. And now, this is topological gravity, but it is negligible here. Here is phi, this is covariant derivative. Here is usual Lagrangian of SO2 you see, we have no standard model here. It is a scalar field, Wi-Fi, which is vector, and phi I is a joint representation of SO2. It is the result of line unification. Next, please. No, this is about topological term, Gauss-Bonnet gravity was this RR. But it is not interesting, it is negligible. What is interesting now is that this action has minimum, has verb, this Wi-Fi has verb, and this verb square is equal to R0 divided on 3, and R0 is a constant density space-time background charge. It's very interesting. That verb is determined by gravity. Next, please. And we have such a relations with gravitational constant here. I'm sorry, but I can't speak in details. It is very difficult. But we relate this gravitational constant with G, the parameter of gravity unification, V. Here is Baer cosmological constant. Here is Baer coupling constant of the weak interaction. Now, how to estimate? We estimate this next. But in this paper, next, we consider the running of alpha 2, and running alpha 2 gives weak interaction coupling constant. And at Planck scale, next, is what's this? The inverse alpha 2 is 50. Then G unit is 0.1. And if we use Planck mass, then we can consider what is VEF. And VEF is huge. VEF is 10 to 18 GeV. It is the second vacuum, not our vacuum, because we live in electroweak vacuum, which is small. Next, please. And now, in contrast to Lise Small and Speciale, which didn't consider mirror world, we consider mirror world. And mirror world first was suggested by Li Yang to restore left-right symmetry, but then Kovzelev from Miranchuk introduced the terminology mirror, meta mirror world, and then, next please, and then also assumed that mirror world is hidden world, which interacts with our ordinary world only by gravity and very small, maybe very small scalar field interaction. Next, please. And but if you have mirror world and mirror particles, then densities, if they are identical, then densities are equal. Please. I will have. And then the density might be equal, but I'm sorry. It is in conflict with astrophysical measurements. I'm sorry. Astrophysical measurement gives that dark matter is 5 times larger than matter. It was assumption by Mohapatra that mirror world is constructed from mirror particles, from mirror baryons, from mirror stars, mirror galactics, mirror halos, mirror planets, everything mirror, and this is dark matter, which we don't see only by gravitational lensing. Yes, by gravitational lensing. And if you have this means that the mirror world is not identical with our The next, please. And please, Erwin's reference foot Leo Volkers, Bergiani Dolgov Mahapatra, and Bergiani's review. It was suggested that effects of Higgs tablets, standard model with that, are different in the mirror and our level. They are different, please, next. And see, next. And we have violation of mirror parity. And this violation is characterized by the parameter zeta, which is the ratio of Webb's mirror and ordinary. And they showed in this paper, especially in this, that zeta is large. Zeta is more than 30. Zeta is of order of 100. Next. But this means that all particles are 100 times, zeta times larger in mirror. You have quarks and leptons and all particles, not baryons, because baryons are, composite. And now you have not standard model, but in large standard model you have universe with two wells which has standard model in our world and standard model in mirror well. Next, please. And then we have such a universe action. You have here Lagrangian gravity, Lagrangian standard model, Lagrangian mirror. Well, and a mix. What is a mix? A mix is the interaction between it is interaction between mirror and ordinary. What is it? Then gravity is here, but what is it now? Next. And then please. And then in the paper, food compatible. Food is Australian physicists. Australian physicists. They considered the interaction between ordinary Higgs field and mirror Higgs field. And this interaction given by alpha is very small. Next, please. Next. Of course, now we can consider the action of mirror weld. It is not difficult. If we replace action by it is common, it's always full stop. I don't know this computer's tricks. We replace by mirror fields. Yes. The next. Then that. And now what has happened? If we consider random dynamics, it means that the nature has used some symmetry. We assume such a symmetry, gravity on U4, where U4 because we need fermions. But I'm sorry now I shall not speak about fermions. They are in U4. You can see our paper in archive. This is new archive paper with Nielsen and Duran. And next, please. But gravity equation after Big Bang, very quickly, maybe 10 minus in degree minus 46 seconds, gravity equation was broken. And we have gravity, and it is for ordinary. The same is for mirror. U4 goes to also is broken during inflation in such a way. And as a result, we have gravity on standard model. The same is in mirror. Please, next. But then, it's very interesting situation now. I'm sorry you are tired, but I don't know. That LHC shows such Higgs value, because people consider this, that it leads that the standard model is valid up to Planck scale and nothing supersymmetry. If supersymmetry is absent, or it is, or breaking of supersymmetric scale is more than Planck scale. Next, please. And some time ago, the multiple point principle, I shall remind you, was applied by Froget and Nielsen, who received, who, using this multiple point principle, they predicted top mass and Higgs mass. And it is very interesting that in half a year, this value was confirmed by experiment, but this is not. LHC gives you 126. The next, please. Yes. Next. What? This is picture which was considered by Froget Nielsen. You have effective potential, Higgs effective potential, and they have two mean. Of course, it is not correct because new vacuum is very narrow, and this is it is illustration. And you see that here you have our vacuum, electron-weak vacuum, in which we live. But here is Planck scale vacuum, second vacuum. We have two vacuum, and all of them are tangentially cosmological forces. That is vacuum energy density 0 here and here. V is 0. Next, please. This is crucial. And then these people consider that our vacuum gives correct Higgs mass if top and Higgs lie on stability, vacuum stability curve. What does it mean? Because we can consider not this, I don't know, not this, for example, not such a, no, such a situation, but we can have such a situation. This is first or second. Such a situation, maybe negative here. You see, if Higgs potential is negative, vacuum is not stable. But then, next, these people considered the 2-3 loop radiative correction and showed that Higgs is 126. Then radiative correction gives you very good Higgs mass. So, the idea of multiple point principle is correct. Second,
We have
please next.
5 minutes.
Huh?
We have 5 minutes. 5 minutes more for you.
Oh, it is very, maybe 10, possible 10.
Okay.
Because annotation, but please, yes, and then, please, more. What? Please, more. 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 What we have now, if we use the Kravievik action and consider an inflation, please, next. have second vacuum, which is at a very high wave 10 to 18 GeV. And this part 5 can be represented in such a way, V plus sigma. And sigma decays during inflation into standard model doublets of Higgs. Doublets. And then if this it is inflaton now. And if this inflaton is trapped in the second vacuum, it can't go out, because tunneling effect is very small. What to do? And then you can see the theory by Andrei Linder, hybrid model of inflation. What means? You must consider second scalar field, which is as a clock field, and gives helps this Higgs field go out, because if this and we considered in our paper, it is our idea, that this second field is mirror Higgs boson, and then mirror Higgs boson interacts with phi, and the bottom rises up, and Higgs boson decays rolls down to the first one. And then, next is what we consider now this expansion in powers sigma divided from B. B is wave. Next please. But and we receive such a thing. But if you see, I'm sorry, vacuum energy density, which is very huge, because lambda 0 is V squared. It is huge. Oh, here we use next. Here we use this CDAX, non-commutativity, what is contribution. And we show that new cosmological constant is small. Next, please. And then what is it? You have quantum fluctuation of cosmological constant, quantum fluctuation of all fields in the universe. But then you have such a lattice-like structure from scalar field, and this scalar field is this varpar, our varpar, and it cancels this cosmological constant and gives the parameter of lattice-like structure as Planck length, please. And no, here you see how lovely it is. Quantum fluctuation has this scalar non-commutative. This can cancel, but this can give, as Sidharth considered, is given by primordial neutrinos. And primordial neutrinos gives you small cosmological constant. And then the next. And we have now not lambda as in gravity, but such a lambda 0, which is 0, and just as in multiple point model. You have V, you have this, Higgs potential 0 at the second vacuum, at 0 at the out vacuum. And we can, and the inflation comes because we have mirror Higgs boson, and they interact and gives us the inflation. And if you want to And now people, what now, only I tell it, then I finish. People made a lot of papers, maybe 50. I can't refer now all, a lot, to have, to describe consistent theory of inflation. Prediction Frogod-Nixon with gradiented corrections, prediction this mass of Higgs and top, and also cosmological parameters. Cosmological parameters are number of e-foldings. This means how what expansion had our universe, and also amplitude of scalar perturbations, and R, this tensor to scalar perturbation ratio. This is and they consider the disagreement, no agreement. But this is quite new inflation. They didn't consider scalar, mirror scalar boson. They considered some hypothetical scalar field. Scalar, not Higgs double. And so, but we, next please, please next. One, we consider this e-folds and estimated, and we consider the agreement between this and star is 50-60 from astrophysical measurements, and zeta by Bereshiani is of order of 100. Next. And we consider that alpha, it is the interaction of ordinary Higgs with mirror Higgs, and lambda is interaction of ordinary Higgs. What this relation gives you the explanation. And then you have no disagreement with cosmological parameters and our maybe conclusions I should make. That's all.
Thank you. Most nice.